All right, so today we're going to look at a few worked examples. Today, let's look at the uncertainty equation, single muscle problem, where we look at the delt doing a raise, a delt raise with a cable. The cable is going to give us a known angle or known weight vector for the arm. So let's get started on this uncertainty equation. Let's say that there is some type of pipe coming out of the wall, and that pipe has a rigid connection, and that there's some kind of force here acting, let's say for now, it's just some vector in an arbitrary direction, and we'll call it f. And then we'll have some length here, and it has some arbitrary direction L1 and L2. Okay, so step one of uncertainty equations, right, is to make the system of equations with all variables. So instead of plugging numbers in, we're going to basically write a list of variables and solve the problem with only variables. Even if the numbers are given, say L1 is equal to 1, 2, 3, or actually 0, let's call this a 2D problem. And L2, let's say that's 3, 5, 0. And then F is given as 30, 0, 0. So that's or say that's just 1, right? Say that there is some tiny amount of direction in the y, deflection in the y direction. Okay. So we need to take all of the stuff that was given about this problem, right? And we need to make variables for each one of these guys, each one of these vectors needs to get a variable associated with its quantity. So let's do L1 is equal to A, B. L2 is equal to C, D. And then F is equal to EF. And let's say that we know that the uncertainty of each vector, has some percent error. So let's say plus or minus some percent uncertainty. You can also write that as sigma L2 vector, right? But we can just make this a variable too, right? We could say this equals plus or minus g, this plus or minus h percent, plus or minus I percent. All right, so let's go move that down. And step two, well, we haven't finished this yet. We need to make that system of equations, right? So we know, oh, I didn't ask a question. So let's say the question is, what is the uncertainty in the moment about A in the J direction? Right? Let's just say actually the K direction because I know that one's going to exist. All right, so let's solve for the moment about A. So how we do this, we go moment about A is equal to some, let's go ahead and just write a vector from A to F, right? So let's get this vector AF, it's called RAF. And if we just say RAF cross F, then we'll get the moment about A. All right, so how do we got to build RAF. So RAF is equal to L1 plus L2. All right, so that's going to equal, if we would just write this out again, we could say L1 is 1, 2, 0, and L2 is 3, 5, 0. And then we want to take the sum. So RAF is equal to 4, 7, and 0. Right, so let's just ignore these zeros, actually. So RAF is 4, 7. So if we take moment about A is equal to 4, 7. Well, let's keep the 0 because it helps with this cross product deal. This is RAF cross F. Put F right here, 30, 1, 0. All right, so check this out. When you do a cross product, if you write it out like this, you can say that anything here multiplied in like the columns, right, is equal to 0. Is basically cancels that because you get I cross I, which is 0. So you can basically ignore anything where you multiply these things in the column. So that's a 0. So this is going to be an I cross J gives you positive K, and that's 4 times 1. Okay, in the K direction. And then let's see, 4 times 0 is 0. So now it's 7 working backwards to I, J to I, and we get a negative K. So 7 times 30, negative K. And then here it's 7, 1, J cross J is 0. Okay, so then these two together give us MA is equal to 7 times 30 and then negative K plus 4 in the K. All right, so that's 210. That's 4 minus 210. Right? So that's the nominal. This is going to be our not what's called nominal. Right? And that is going to be equal to MA is negative 206. But remember, we wanted that we wanted the uncertainty too. We wanted to know what is the uncertainty. Right? Okay, so to do this, we've got to redo all this cross product business, all that stuff. We got to redo it as only variables. Okay, so now MA is equal to, what is it? Well, it's RAF cross F. How do we write that? Well, RAF is going to be equal to A plus C, right? A plus C and B plus D. That's in the I direction, B plus D, B plus D in the J direction. And then F is going to be EF, right? So we'll do EF. All right, so remember this is an I direction and this is the J direction column. So it's going to be A plus C cross E is 0 because I cross I is 0. I cross J is going to give you a positive K. So A plus C times F in the positive K direction. Then we get J cross I for B plus D with force E, and that's going to be in the negative K direction, right? So those are pretty easy equations, no big deal, right? So if we wanted to find the uncertainty in the K direction, you know, we need to do the summation of the K's, right? So we gotta get moment about A is equal to A plus C F minus B plus D E. Cool. So remember the uncertainty equation we looked at last time, and that was this this guy here. So let's rewrite that. Now we look at the uncertainty. And it says that this uncertainty sigma about something is equal to the square root of the partial of something with respect to each variable in something, right? And this has got to be the summation of all this stuff. So this stuff squared times the uncertainty of each variable squared. So if we know the uncertainties of each component, xi, in something, right, then we can get the uncertainty of that something. So in this case, we're looking at the uncertainty of the moment about A, right, in the k direction. Okay. And we know that equation that's given here, right, because this is all k. So all this stuff belongs in the k direction, right? So if we were to try to take the uncertainty about MA here, we would need to plug all of that stuff into this summation, right? Into this partial of this, all this equation, right? All that stuff. And then do the partials with respect to each one of the variables. Okay, so let's do that real quick. Oh wait, so this is the point. We need to find this uncertainty for each one of these variables, right? And how we do that, okay, that comes from this stuff, right? Plus or minus g%, h%, I%. All right. Okay, so let's go ahead and just let's write all this stuff out. So let's go say partials in one area, right? So what do we need to look at? We need to look at partial of MA with respect to A, do partial MA with respect to C. And let's just, I mean, we could just write all this stuff out. Right? Okay, so let's actually look at this equation. It says, if we want to write all this stuff out again real quick, let's do it. Let's say that's AF plus CF plus minus BE minus DE. And that's the k direction. Okay. So the partial of MA, this equation with respect to A, is equal to, right, it's the derivative of each component with respect to A. So that's DAF over DA plus DCF over DA minus DPE over DA minus DE over DA. Okay, so with respect to the variable A, we know that CF is a constant. That stuff gets canceled. So all these constants get canceled. And then D of AF with respect to DA, that's kind of like, remember that F is a constant, gets pulled out, right? So we get F times DA over DA, right? And that equals F. Easy peasy. Okay. So then if we do B, that's this one, we can just say that that's going to be negative E, right? I mean, that's pretty simple. Let's do C. Well, that's going to be F again. D, I mean negative E. Okay, what about E? So E is negative B minus D, because you're going to pull all that stuff out, right? Remember that we can just look at this this one up here again, and this is the constant term, right? This will be the constant term, and that'll be DE. That'll just go to 1. So it's going to be B plus D. It's equal to negative B plus D. Okay. And then F is going to give you A plus C. So those are super easy partials, right? Let's say, what's the uncertainties? Say, what's the uncertainty in A? Just line these things up. Uncertainty in B, uncertainty in C, uncertainty in D, E, and F. So if we come up here, uncertainty in A belongs to L1, and L1 has a total uncertainty of plus or minus G%. So then the uncertainty in A is just going to be A times G percent, right? And then B, same thing. So it's going to be B times G percent, C times H, T times H, and that's E times, what was it? Yeah, it's I percent. Okay. All right, so let's just assemble this equation. Let's just use this whole thing and all the stuff we made, all this stuff. Let's make a big equation for the uncertainty of MA. Okay. So the long form uncertainty in MA in the K direction will be equal to the square root of a bunch of stuff, right? It'll be, it'll be partial MA partial A squared, sigma A squared, plus partial MA squared, B sigma B squared, partial MA squared, partial C sigma C. One more. All right, so now we've expanded our little uncertainty equation, and we've done that for every variable in our equation. Okay, so let's just go plug and chug it, right? This one, MA squared over A is going to be F. So that's F squared sigma A is A times G percent squared. What's this one? B. B gives us negative E, but it's all squared, so we don't have to write that, right? Because the negative goes away. Sigma B is times B times G percent squared. Keep going, let's go. C, right? What's the C? Is F again? F squared C times H percent squared. All right, I'm not going to do the rest. The rest is easy, right? You just plug all that stuff in. At the end of the day, say for example, I gave you F is equal to 30, right? Actually, I think I gave numbers, right? Hold on. Yeah. F was 1, E was 30, all right? 1, 2, 3, 5. Okay, F equals 1. I think A was equal to 1. And then let's say G is equal to 10%. So that's 0.10, right? So what do we do? It's going to be 1 squared times 0.1 squared. Cool? So then you would just plug all that stuff in, right? All this stuff is plugged in. All right, let's go. One more. So E is equal to 30, I think. B was 2. And then remember G is 0.1. So then that would be 30 squared times 2 squared times 0.1 squared, right? So that's that one. Yeah, and then you just go ahead and after you get all of these, you sum them all together and you square root it. And that's your answer for sigma MA in the K direction. All right, a lot of work, but it's really easy stuff, right? It's easy work. So let's review it again real quick. So I give you, what do I give you? I give you this plus or minus, let's say that was, what was it, 10%. This is plus or minus, say, 5%. And this is plus or minus 20%, something like that, okay? This is something I would give you. I'd give you a vector for L1, L2, and F, and I'd say that vector varies by 10%. So each one of these components varies by 10%. So then your first step would be to go ahead and solve, or basically take the numbers that I give you and make them all variables, right? So L1 is A, B, and the uncertainty in L1 is G. L2 is C, D, uncertainty is H. F is E, F, uncertainty in I, right? often I'm going to ask you to just find the nominal term. So it says MA is negative 206. And then you'll have to go do all of your math in variable term, and then find the uncertainty through these partials, right? Okay, so I'm never going to ask you to do difficult partials. It's always going to be pretty easy stuff. All right, so now let's move on to this whole single muscle problem. All right, so let's say the question is find the reaction forces in the glenohumeral joint due to delt cable rays. Right. So we know that there's a ton of different muscles. There's just way more muscles acting on this thing, but these problems get complicated really quick. So we're just going to simplify everything and say that the delt, says like most of the work is done. So we're just going to make that assumption. All right. So again, all we're given is this little picture here, and someone asked us to analyze the reaction forces in the basically the shoulder joint, right, to due to this cable rays, right? And say we went in and we measured this angle, right, and we said that that angle was something like 55 degrees from some floor, right? So if we call that the floor, that's 55 degrees, right? And I want to assume also that this person is kind of standing straight up and down, right? There's a symmetry with this whole system, right? This whole person's kind of standing straight up and down, and the shoulder extends out at some other angle, which is also measured. We measured that somehow. So we got this one, call it phi, right? So, right, these are all things that we would have to consider when we do our analysis. Say phi here is like 10 degrees. Okay. So where do we start? And that's always a great question, right? Because there's a lot of different ways we could go about solving this. And again, we're trying to solve for the reaction forces in this joint right here, say. So it doesn't make sense to study the clavicle in this case. Probably not. I mean, the delt does insert on it, so there is some force chain there, right? But the weight is coming, here. It's the weight's coming from the hand, right? Get some force vector. Let's say that magnitude of the force is known. We looked at the weight pulley system and said, oh, that was 50 pounds or something like that, whatever. All right, so we always have to look at where are we analyzing these forces from? Like where are the external forces acting on the body that we're trying to analyze? We're trying to use as part of our analysis, right? Because there's ton more forces too, acting on this joint, right? There's the lats, there's the pecs, right? All these forces are inserting on this thing, but we're just going to ignore it. We're going to ignore it because our goal is to talk about this delt, and we're making the assumption that the delt does all the work, right? Okay. So in that case, right, we want to look at the simplest way we can connect the reaction forces to the external force of interest. In that case, that's this force that's going through the hand, through the radius and ulna, through the humerus, and the delt is rotating everything up, right? Okay. So this is going to be what's called our system of interest, right? What I just highlighted. Okay. So our first step, really, we'd like to make mechanical drawings or engineering drawings that describe this full system up to the thing we want to solve for, right? That's the reaction forces in the joints, right? So make engineering drawing of our system of interest. Okay, so that's easy. Right? You gotta take this, let's just take this whole thing I just now drew. It's like a kind of one of these deals. Let's say that force comes from the end of this at some angle. And we don't need to draw the angle or anything if we have the vector. So if they have that vector hat, we don't need to talk about what this angle is with respect to anything because it's given by that vector. So remember, that vector is of magnitude and direction. Now we're also going to put in this thing, it's like the delt muscle insert, right? And we're going to, so it's going to be some tension cable. Tension cable, wow. Okay. So that tension cable is going to come like this, and then it's going to insert on something else, and we're just going to say that that something else is now, it's a rigid wall. Okay. We're also going to replace this joint, this shoulder joint, with a pin. So we're just going to draw a pin here, and the end of the pin is connected to the wall. Okay, so next, really all we need to make this complete is give ourselves a bunch of points. So let's say this is A, that's B, C, D, and then we need to describe the lengths. So one way to do lengths is to make a big coordinate system, a grid. We could do that, where here's a big grid, and talk about this is, you know, this is a known if this is a origin, 0, 0, then we can just talk about these things and project them, right? Where do they act? Something like that. The other way we can describe all of that is just to write a vector. Let's call this RCD. So okay, so RCD, and then we got our AB. So either one's good, right? As long as they're vector form, we're okay. And in fact, if they're already in vector form, or I give them to you in vector form, that's even better, because wait, we need one more. We need C, B. Okay. If I give them to you in vector form, you don't have to do anything like any transformations or anything. I'm basically, if I give you RCB, I'm giving you the distance from C to B in this direction and C to B in this direction, right? I mean, that's basically what that vector would be. All right, but this isn't complete without a description of RAB, RCB, and RCD, right? So AB, RCB, RCD, and F. Let's describe these things. Okay. So RAB, that would be kind of like this, where the delt connects the clavicle, where the delt connects on the humerus. All right. I don't have that information on top of my head. So I'm going to say that A, the location of A to B, right, must be some positive value in the I direction. And I'm going to say that just is going to be A. It's going to be a negative value in the J direction, which we haven't described yet, actually. So let's just describe this as X, and this as Y. And let's say the origin is at our joint, right? It's somewhere at our joint. We could even put it so 0, 0 acts at the joint. That might be convenient, right? We can do anything we want. This is our deal. All right, so then the distance from A to B is described by AB. Okay, RC to B. RC to B is going to be something like positive in the I direction, positive in the J direction. So I'll just write that as CD. RCD, that's going to be positive and positive. So EF. F, I know that it acts in the negative J, negative I. So let's say our components here are going to be like negative G and H. Okay, so we described everything fully. So step 2 is an FBD. So let's take this whole thing. Make a rod. So we could just kind of make something like this. In fact, this whole thing, to be a better mechanical drawing, should just be a rod. It should really just be drawn as some kind of beam. We always want to draw the simplest object we can. So let's take that beam and draw all our forces. We got some reaction force. Let's call that reaction called S. There's some delt reaction here, so I call that D. Okay, so then we still have to talk about these lengths, these vectors. S2 there. That's C, B, D. So R, C, D, R, C, B, and F. All right, so now we don't need RAB anymore. that really what that did is it gave us the direction of D. That we can say that D is equal to some magnitude of D times the direction of D, and we know the direction of D is EF. So that's EF divided by the magnitude of EF. Right. So we also know that these muscles can only act in tension. So we need to consider the direction going negative. It has to go. The direction has to go in the negative X and the negative. Actually, it's positive J. Because B was flipped. Right. So that. Oh, I did the wrong thing. So it's A negative B, A negative B. All right, so this is AB over the, the magnitude of AB, and then times the magnitude of D, right? So that gives us the vector of the force D acting on that bone. It's not really just a bone, it's the whole arm, right? We're talking about the whole length of the arm here. All right, so now we got to put our little coordinate system deal in. And let's list our assumptions. We got gravity free. We got rigid body and static equilibrium. Okay. So now S we don't know the direction it acts, right? We have no idea what the reaction directions are. So here's a rule for you. Always just assume the reaction forces are positive. Okay, even if you know they're not. Then what's going to happen is that once we do all of our analysis, the sign of S will pop out. All right, and if we chose S to be in some other direction and we said it had some negative component in X or something like that, and then it turned out to be a negative of that, it's all going to be really confusing. But if we just choose it all to always to be positive, at the end of the day, it turns out that the X component of S is negative, then we just draw that vector and the going left. We draw it in the negative x direction. Okay, so rule is always just assume the reaction forces are positive at first when you do your analysis. Okay, so that's let's go step 3. That's sum of forces. So here we can do we got this table we can make where these things are I, J. These are going to be the forces. So let's say this is F, D, and S. We make our table like this. Remember I told you F is going to be negative GH. All right, let's make everything real easy here. Actually, let's copy this. Okay. Negative GH. That doesn't make sense. That should be negative H. What happened? So then D, right? D was all this mess. So let's just call that mess something else. Let's call that I and J. And we know that I is negative and J is positive. And you might be asking, like, hey, we just talked about this rule deal, right? It's like, what? I thought D was kind of a reaction force. It was kind of like one of these things we don't know. It's unknown. But we should know the direction of D because, remember, we're assuming that all muscles always act in tension. And from that assumption, it says that any reaction on our little free body must be in the direction of the muscle. There can be no moments or anything. It can only be a force in the direction of the muscle. So that allows us to put the signs onto D and be very confident about those signs. So that's negative I. Actually, because we did IJ, that's stupid. To KL. Actually, not K either, huh? LM. And that's going to be negative L and M. And then let's call S something. Let's call S. S equals, well, we can't do NO because O looks like 0. So we'll call this NP. It's NP. So sum of forces equals 0. Let's say negative G minus L plus N equals 0. Negative H plus M plus P equals 0. And let's call this equation 1 and equation 2. All right, so our goal is to make as many equations as we can, right? So let's go step 4. We gotta do sum of moments. All right, so we always have to choose what's the best place to take a moment, right? And if we take it at B, then the D cancels because moments about something on a similar line of action produce no moment. If that, if the force is on the line of action of the moment, that force contributes no moment at the location. Okay, so we obviously want to take a moment about C, right? Because nothing else makes sense. If we did about D, then we would get some relationship between S and D, and that would be no good because we want all of our relationships to have as many knowns as we can in them. So we're going to take our moment about C. So let's call this a moment table. We're going to come R, C to D cross F. And we will do R, C to B cross D. Okay, so RCD cross F. Remember, if we would just write this stuff down next to each other and cross them, actually becomes pretty convenient. RCD is EF, and F is negative GH. So what is this? This is EH. We went from I to J, because this is this table I, J. We went from I to J, we get positive K. So in the moment, let's make this table IJK. And then we'll write down our first thing, which is that we get EH, K direction. We got EH here. Remember that E, if we do EG, we get I cross I is 0. And we get JI, we get F, G, negative, and the negative K. Okay, so that's another thing we can write down. We can say that's plus FG. Now let's do RCB cross D. That'll be C, D. D was here, LM, negative LM. Okay, so CM, that's the I, that's J. It's CM, K. DL, DL, K. No, negative K, negative DL. So that's CM plus DL. Okay, so we got all of our moments done now. Sum of moments about C equals 0. That's 0, 0. And this is EH plus FG plus CM plus DL equals 0. This equation 3. All right, step 5. It says, do we have enough equations for our unknowns? So let's make a table real quick. Say unknowns. What is our unknowns, right? That's going to be S and the D vectors. So unknowns is negative L. We got M, N, and P. So that's 4 unknowns and 3 equations. So no, can't solve. Okay, so now what do we need? We need, if no, we need some more relationships. Sometimes, you know, this is like the hard part, right? Getting these ideas. And, you know, for the multiple muscle systems that we talked about last time, you know, we came up with some ideas how to relate muscles and forces to each other based off of expected magnitudes and such. But in this case, right, we're going to say that D makes some angle, D makes some angle here, theta or something. Let's call that, maybe theta is better. So D makes some angle theta with everything, right? So if we want to draw this real quick, we'll sketch it here just to have a good reference. We gotta make our little triangle. Right? Say that that's D. And if this is the XY coordinate system, then what does that mean? Well, if we just look at this, put D projected out here, that's kind of the same thing, isn't it? All right, so, you know, don't worry about it though. Like, yeah, this is alpha. Well, let's call that thing alpha for now. The phi, stuff like that. But what we really care about, right, is this angle right there. We can call that gamma. And we can get gamma because remember how we described this whole thing. It's all these like vector A to B, right? And that whole thing, we know we described it in the XY coordinate system with this A and negative B deal, right? A, negative B. So, you know, if we really wanted to figure out what gamma is, we know this is A, we know that's B. So we could, you know, we could talk about, so So this is an opposite divided by adjacent is equal to tan. So tan gamma is equal to b over a, and gamma is equal to tan inverse of b over a. Cool. So then gamma's a known. That's all I want to make known to y'all. Right. So then the relationship between, let's call that this whole thing again. Let's say that's D, and now we want the vector components of D. Right. This is all like RAB stuff to get gamma. But if we wanted to actually find the components here, which is negative LM, right? We want to know L, and we want to know M, and we know gamma. So then we can write let's make this relation with D. Magnitude of D is the hypotenuse here. This whole hypotenuse is the magnitude of D. So magnitude D, again, let's do the SOHCAHTOA deal. Opposite over hypotenuse. M over D is equal to sine gamma. Cool. We got L over D is equal to cosine gamma. So then let's use these two things together to make a relationship between all these things, right? We'll do that through D. So we'll solve for D. D is equal to M over sine gamma. And we'll use this and plug it in there. So now we have L over M sine gamma is equal to cosine gamma. Now we can do, let's say we solve for one of these deals, like L. So L is equal to M cos gamma over sine gamma. So this whole deal is then M cotan gamma. And we'll make this whole thing equation 4. Okay, so we're chugging right along. We got all of our equations. We got 4 equations, 4 unknowns. Time to move on. Step 7. System of equations. Okay, let's grab all of our equations that we know. L equals M cotan gamma. Okay, so once we get to the system of equations, we want to look at what is known here. What can we use to solve for all this stuff? So G and H are knowns. So G, let's color these things. G and H are knowns. And then now let's identify like the easiest path to going through and solving for all of these different equations. So one easy way is to take this guy and plug it in somewhere else. All right, so look, all of these are knowns, A, B, C, D, E, F. Those are all knowns. All right, so look, all the colored stuff is known. Plugging it into this equation there gives us the quickest way to make one of these other variables kind of solved. All right, but to do that first, I want to just simplify this whole thing. Just call that, like, let's call this big A or something. So now, solving, we got L equals MA. We have, if we plug this whole thing into there, we have EH plus FG plus CM plus D big A M equals 0. All right, so let's make another one then. Let's make another simplification here. At EH, and I don't want to do all that stuff again, so I'm just going to write this as B. And then I'm going to say C times a bunch of stuff, M plus DA, no, sorry, MC plus DA equals 0. We'll make this stuff even easier. So now this is M is equal to B over C. So there's my equations. Okay, so plug that stuff into these. We got L and M. These are now knowns. Now let's solve for N. N equals G plus L is M A. And now I'll solve for P. We got P is equal to H plus M. And then now look, we have to reorder these things. These equations, we have to reorder them a little bit because M is a function of all the known stuff. So let's plug this in here. So solve this one first. Then that gets plugged into here, MA and G. And then we go along and solve for everything. Step 8. Step 8 is going to be so in step 8, say all these things were numbers. You go ahead, come back to whatever you draw. Okay. And when you plug in the components here, the components M, N, P, L, right, so S was NP. And we have D. And M. L. Okay. All right, so now when you solve for all the magnitudes of these deals, you plug them back in, and you got to see if they work. Do the directions make sense? What was that one? It was GH. Okay, so you got to ask, do the directions of NP make sense. If they don't, there's something going on where you missed a sign somewhere, something like that. All right, so that should be it. I mean, that's going through these type of analyses. I did that all in variable form. Okay, so say I wanted to do uncertainties of everything, I can do that because I go through and say, I had uncertainties in these variables, say something like that, and then I want to see the uncertainty of the result. I take all these equations, do the partials. That's how I would get my uncertainties for my reaction forces, N and P. Right? My reaction force N has G and M times big A. Big A was C times D, or big A was cotan gamma. Yeah, so if I wanted to do my uncertainty in the reaction forces N and P, I would take these equations and put them into my uncertainty equation. Right? That's the summation. That's the square root of the summation of the partial N with respect to each variable squared times the sigma of each variable squared. Right? So here that wouldn't be very hard. It would be I would have to have G in there, I would have to have M in there, these kind of things. Right? That would be a lot of work to do that, but if you wanted to do it, you would use these equations for your uncertainty. Okay, so next class we're going to talk about multiple muscle systems. It's essentially the same type of analysis, except for there's now going to be like a muscle here and a muscle there, something like that, right? Say muscle there, and they're all acting in like different directions and things. So we want to know what's the resultant, what's the resultant forces at some joint or something, given all these different muscles. All right, cool. See ya.